Hello friends, welcome to my YouTube channel. Friends, in this series of tutorials on HFD and BMD, today we are going to discuss a new problem on cantilever beam for gate purpose. Friends, the topic of SFD and BMD can be learned only through solving problems. I am going to upload 50 problems on SFD and BMD, and if you go through these problems, you will never find any problem in future regarding SFD and BMD, especially in GATE exam. The sign convention are universal and taken from standard book. For more information on sign conventions, refer to the link of the video in the description box. So without wasting any time, let's start this video. Okay. So this is the cantilever beam and there are 2-point load. One is acting at point B and another one is acting at this point. Now we have to draw the shear force and bending moment diagram for this portion of the cantilever beam, that is CA. Okay. Now first step is always to find the reaction at this point A. But before, we have to simplify this diagram and convert it into an equivalent diagram. So see here how I am converting this. Now this load W is creating a movement in this direction, okay, clockwise direction, okay, and having a magnitude. So this is the length L actually, friends. I forgot to mention it. This is the length L. So it is creating a movement of magnitude W, this load W into length L, okay, about this point. Now this movement can be further transferred to here and it will give us how much? W into L at this point C. This movement is being transferred here. So we can generate the diagram as follows. So this is the equivalent diagram that I am drawing here. This is the point C, this is the point B, and this is the point A. Okay, and here a movement having magnitude WL is acting like this at the point C, and this load W can be transferred without affecting the system at this point C. Okay, like this. So this is the new diagram and it is equivalent to this diagram. Okay, so we can draw the bending moment diagram and shear force diagram for this figure very easily. Now let us look how we will do that. Now first thing is determining the net force that is acting over this cantilever beam. So the next external force acting over this cantilever beam are these two loads only. That is the vertical force we have to look at. So these two vertical loads are acting. So W plus W will give us 2W in downward direction. Okay, W plus W in downward direction. So the reaction at A in vertical direction will be equal to this F net and will have magnitude 2W, this 2W, and will go in vertically upward direction opposite to this direction. Okay, so I am showing here RAB acting at this point A, that is the reaction force acting at this point A. Now the net moment acting at the point A we will calculate because of this force and this concentrated movement. Now because of this concentrated movement, there will be a movement of WL acting at this point A in clockwise direction. So WL will cause a movement of magnitude WL in clockwise direction. This force will produce a movement of W into this length. This is 2L and this is 2L. That is W into 2L plus 2L, 4L in anti-clockwise direction, because it will try to rotate this beam ACA in anti-clockwise direction about point A, this vertical load. Okay. Now because of this also the the moment at point A will be equal to W into this distance 2L. Okay, and it will also create movement about point A in anti-clockwise direction. So the anti-clockwise will cancel out with clockwise and we will left with how much? 5 WL in anti-clockwise direction. Okay. Now the reaction movement at A will be equal to net movement at A and will be equal to 5WL. That's it. It has same value as this net moment and will act in opposite direction, that is clockwise direction, opposite to this direction. So we will show here the reaction movement at the point A. So at the point A, it will go in like this, okay, having magnitude 5WL in clockwise direction. Now friends, we will draw the shear force and bending moment diagram by finding out the shear force at various points A, C, B and A. Let us first find out the shear force at the point C. Now because a point load is acting at point C, that's why the shear force will change when going from left side of the point C to the right side of the point C. So we will calculate the shear force on the left side of the point C, okay, and shear force on the right side of the point C, okay, where L denotes the left and R denotes the right. So on the left side of the point C, if you want to calculate the shear force, then we have to construct a section on the left side of this point C. Here I am rubbing this for clarity and making visible it here. That is, it is acting at point C. Now having magnitude, how much? This magnitude is WL of this moment. Now I will construct a section on the left side of the point C. Suppose this is the section that I am constructing over here. Now we know that from the definition of the shear force, that shear force at any section is the sum of the algebraic sum of all the forces either on the left side of the section or on the right side of the section. So you can consider any side. I am considering here the left side. So on the left side of the section, you can see that there is no force being terminated at this section XX. So there will be zero shear force about this section XX. Okay, now we will find out the shear force on the right side of this section C, right side of this point C. So for that we have to construct a section again on the right side of the point C like this. I am constructing here this section XX. Now if you look on the left side of this section, then you can find that there is only one force which is accounting for the shear force, which is the load W, and because of this load W there will be a shear force of magnitude W and having negative sign, okay, because this force W is creating a anti-clockwise rotation of this beam element which is lying between the point C and this point which is lying on the section XX in clockwise, anti-clockwise direction about this point, okay. So that's why it is treated as negative anti-clockwise rotation, okay. Now because of this concentrated movement, there will be zero shear force at this section XX, because concentrated movement do not contribute toward any shear force at this section XX. Now we will calculate the shear force on at the point B. Now because a point load is acting over the point B, you can see this. So the shear force on the left side of the point C we have to calculate, and on the right side of the B we have to calculate, because shear force will change suddenly when going from the left side of the point B to the right side of the point B. So shear force on the left side of the point B first we will calculate. For that again we have to follow the same procedure, that is we have to construct a section in the left side of the point B. This is the section constructed in the left side of the point B, and looking on the left side of this section you can see that only this force is contributing toward the shear force and give us a shear force of magnitude W with negative sign. Negative sign, why? Because this force W is trying to rotate this beam element which is lying between the point C and this section XX in the anti-clockwise direction with respect to this point which is lying on the section XX. So this is creating a minus W shear force, and this will not account for any shear force. This concentrated movement will not account for any shear force about this section XX. Now shear force we have to calculate on the right side of the point B. For that again we have to follow the same procedure, that is we have to construct a section on the right side of this point C. So this is the section XX constructed on the right side of the point C. Now look on the left side of this section. So there are two loads, this one and this one are lying on the left side of this point B. So you can see that on the left side of this point B there are two, left side of this section XX there are two loads, one is this and another one is this. So this will contribute toward a negative shear force having magnitude minus W, and this load will also contribute toward negative shear force having magnitude minus W. The sign convention I have already told you it is causing anti-clockwise rotation about this section xx, both these forces. That's why they are taken as negative. So it will give us minus 2w. Now we will calculate the shear force on the at the point A. So shear force at the point A we have to calculate. We will calculate on the left side of the point A, and we will calculate shear force on the right side of the point A. Why? Because there is a point load acting at this point A that will cause the shear force to change as going from left side of the point A to the right side of the point A. So for calculating the shear force on the left side of the point A, again we have to do the same thing. We have to construct a new section here on the left side of the point A and look at the various forces which are acting on the left side of this section. So there are these two forces acting only, this one and this one. So because of this force there will be a shear force of minus W, and because of this there will be a shear force of minus W, because both the shear forces are creating a anti-clockwise rotation of this beam about the point A. That's why they are taken as negative. So I will substitute it with minus 2W. Now shear force on the right side of the point A we have to find out. For that again we have to follow the same procedure. We have to construct a section on the right side of the point A, and you can see that the beam terminates on the right side of the point A. This is the point A, and this movement is actually of 5W is lying here. Actually it is going like this and having magnitude is 5W. Okay, I am not writing here because the space is limited. You should understand that this movement has a magnitude of 5W going in clockwise direction. Now if we look at this section XX, on the left side of this section, this force will contribute toward the shear force, this force will contribute toward the shear force about this section, but these two movements will not contribute anything about this section XX in terms of shear force. So what we have to do, because of this there will be a shear force of minus W, and because of this there will be a shear force of minus W. But this force, the reaction RAB is acting at this point A, and this point A is lying on the LHS of this section XX. So because of this force RAB, there will be a shear force at this section XX which is having a magnitude of 2W, because RAB magnitude is 2W. Okay, and it will have a positive sign. Why? Because it is trying to rotate the beam element which is lying between the point A and the section XX. This is the point A, okay, here, and the section XX in a clockwise direction. See this, how it is rotating. If this was our section XX, this is our section XX. I am writing this section, I am drawing this section XX here, and this is the point A. Okay, and at this point A you can see that this RAB is acting like here. So this is causing an imaginary beam element between the point A and XX, section XX. The rotation of this imaginary beam element between the point A and section XX in clockwise direction. So it is taken as positive 2W, this RAB, because the magnitude of RAB is 2W. So that this is the reason. So it will give us zero shear force. Now we will draw the shear force diagram. Now for drawing the shear force diagram, what we have to do? We have to draw an equivalent line which is having the line of the length of C at A up to a scale, and after that we can see that this is the point C, this is the point B, and this is the point A. Now see this, on the lower side of this line, that is below this line, all the shear force are treated as negative, and above this line all the shear force are treated as positive. So at the point C on the LHS, the shear force is 0. It is going to minus W. Okay, here minus W, or on the right side of the point C, and it is minus W on the left side of the point B. Okay, lying in the same level, and it is going to minus 2W. Okay, minus 2W. It is going at the right side of the point B, and it is going to minus 2W on the left side of the point A. So making cross here over the below the point A, and it's going to 0 at the right side of the point A. So joining the first point with the second to the third, and third to the fourth, and fourth to the fifth, and fifth to the sixth. The point between the line between C and B is a straight line because there is no point load lying between point C and B. Similar is true for these two. The line between B and A, because there is no vertical loading line between point B and A. That's why the line of shear force diagram is straight line between point B and A, and it is negative, forming negative area. So this is the shear force diagram. Now we will draw the bending moment diagram. So for that we have to rub these things again, okay? And this moment was our 5W. This MRA was 5W. So I'm drawing this thing. Okay, now we will draw the bending moment diagram. Okay friends, so let us see how we will draw the bending moment diagram. So bending moment calculation will begin from here. So bending moment we have to calculate. Now let us start with the point C first. The bending moment at point C first we have to calculate, because there is a concentrated movement lying at this point C. That's why the bending moment will change suddenly when going from point left side of the point C to the right side of the point C. So bending moment will change suddenly. That's why we have to calculate the bending moment on the left side of the point C and bending moment on the right side of this point C. So if you want to calculate the bending moment on the left side of the point C, again follow the same procedure. Consider a section on the left side of this point C. Okay, now we know that according to the definition of the bending moment, that bending moment at any section is the summation of all the movements either on the left side of the section or on the right side of the section. So bending moment, we will choose the left side of the section. You can choose the right side also, but you have to follow my sign convention because it will make it little bit difficult. So I am going to left side. So on the left side of this section there is nothing lies. So the bending moment is 0 on the left side of the point C. Now calculation of the bending moment on the right side of the point C. So on the right side of the point C, we have to construct a section here like this on the right side of the point C. Now you can see that on the right side of this section, there is a concentrated movement line, because of which there will be a bending moment about this section XX, and it will have a magnitude of plus WL. Positive sign is here because we are following this sign convention that any movement which is lying on the LHS of a section will create a positive bending moment about that section if it is going in the clockwise direction. Okay, so this bending moment is lying on the LHS of this section, that is left hand side of this section XX, and it is going in clockwise direction, similar like this. So it is treated as positive. So it is plus WL. Now because of this force, the bending moment about this section XX is 0, because this distance is negligible, because the section XX is lying very close to point A, that is nearly 0 distance between the point C and the section XX. So the moment because of this force W, that is the shear force, so bending moment because of this particular W will be 0 about this section XX. Now we will find out the bending moment at the point B. Because there is no concentrated movement lying at the point B, so we will directly calculate the bending moment at the point B. Okay, it will give us same result. Okay, so here constructing a section directly at point B. Okay, now bending moment at point B will be given by the summation of all the movement about the section XX because of this force and this concentrated movement. So because of this force there will be a bending movement which will be hogging in nature about the section XX, and will give us a bending moment of minus WL because of this force W, minus W into 2L, sorry, into 2L, that is this load into this distance between C and B is 2L. Okay, and because of this concentrated movement there will be a positive bending moment about this section XX having the magnitude plus WL. Similarly explained in the earlier case, the sign convention of this concentrated movement is taken from here. Now the bending moment we have to calculate about the point A. Okay, so this is the point A. For that we have to calculate the bending moment on the left side of the point A and bending moment on the right side of the point A. Okay, on the right side of the point A. Why? Because there is a concentrated movement acting at this point A having the magnitude 5WL having the moment 5WL in clockwise direction. Okay, so that's why we have to calculate on left side and on the right side of the point A. So for calculating the bending moment on the left side of the point A, we have to construct a section here on the left side of the point A, very close to this point A. But for clarity, I am constructing it a little bit away from it, but it actually very close to this point A. So if you look on the left side of this section XX, then you can see that this force, and this concentrated movement is lying. So because of this load, there will be a bending movement of W into 2L. Okay, W into 4L. Actually, this section is lying very close to point A, but for your clarity, I am showing it little bit far away from point A. So this distance between this point B and this section XX is almost 2L. Okay, so that's why I am writing 2L plus 2L is equal to 4L into this load W, and it will create a hogging bending movement about this point, about this section XS, and hogging is treated as negative. Now look at this load W. This load W will also create a hogging bending movement of magnitude W into 2L, that is W into this load W into this distance 2L between the point B and this section XX is 2L. This section is very close to this point A, but for clarity I am showing it away from the point A. Okay, actually this is very close to point A, so that's why this distance between the section B and section XX will be nearly equal to the 2L. Okay, now because of this concentrated movement, there will be a movement of plus WL. Similar sign convention is followed here. So it will give us how much? The bending moment at point A will be equal to minus 5 WL. Okay, you should calculate by yourself. It will come out to minus W. It is also hogging. Okay, this movement. Now bending moment on the right side of the point A you want to see, then you have to construct again a section on the right side of the point C also. Now you can take on the left side of this section also, or on the right side of this section. See the movement. Now for simplicity, I am seeing on the right side of the section. So on the right side of this section XX, which is lying on the right side of this point A, this section XS, you can see on the right side of this section there is nothing lying. No force, no movement is lying. That's why the bending moment about this section XX is 0. You can calculate by looking on the left side of this section also, following the same procedure. You will find that the bending moment will come out to be 0 using this sign convention, because this force will cause a positive bending moment. This moment will cause, that is the reaction moment acting at the point A, will cause a positive bending moment about this point A according to this sign convention. If you look, if you are calculating the bending moment about XX in the LHS, looking at LHS of the section, but I have looked on the RHS of the section, and you can find easily from the RHS of the section by looking on the RHS of the section. It is very simple. That's why I have done this. You should also done by this, that is looking on the LHS of the section as done in the previous cases. You will find the same results. So now we will draw the bending movement diagram. So the bending movement diagram we have to draw. For that we have to project these points. The point C is projected here over this line, and point B is projected here over this line, red line, and point A is projected here. Now the bending moment at point C is 0, so marking 0 here, which is lying on this line, and bending moment on the right side of the point C is plus WL. We know that on the upper side of this line the positive things lies, and below this line the negative things lies. So the bending moment on the right side of the point C is WL, so going WL in this direction, that is of this point E, we have to go a distance of WL. Okay, and the bending moment on the at the point B is minus WL, so going minus WL here, or below this line, this is minus WL. Okay, and bending moment at the point A on the left side is minus 5 WL, so minus 5 WL will lie somewhere here. You have to choose a suitable scale for it. And on the right side of the point A, the bending moment is again going to 0. So joining first point with the second, okay, second with the third, and third with the fourth, like this, and fourth with the fifth, you will get your bending movement diagram. Now one thing we have to keep in mind is that the between point C and B, the shear force diagram is a straight line between this point C and B. That's why bending movement diagram is an inclined line between the point C and B, and between the point B and A, the bending movement diagram, the shear force diagram is a straight line. That's why bending movement diagram is a inclined line between the point B and A. So this is the bending movement diagram. So this was all for today's topic, friends. If you like my video, you can subscribe my channel and also press the bell icon for the notification of the upcoming videos. So thank you, friends, for watching this video.